Perfect. Okay, so thank you very much for the introduction. I'm going to be talking about a work on formalizing the universal divided power algebra in NIM, and everything that I will discuss is joined with Antoine Chamberlain. So before talking about the universal divided power algebra, I will say a little bit about what divided powers are. So if you have a commutative ring R, you have an ideal in this ring. A divided power structure on this ideal is a family of maps from the ideal to itself indexed by the natural numbers that essentially satisfies the same properties as the family x to the n over n factorial. And if you have such a triple of a ring, an ideal, and a family of maps with these properties, we call this a divided power algebra. So I'm not going to make completely precise what I mean by satisfying the same properties, but to give you an idea, for example, when we add up two elements, we have the binomial formula for x plus y to the n. Then if we reorganize it a little bit so that it doesn't show any binomial coefficients, this is the formula that we get. And then if we abstract the family x to the n over n factorial to gamma n, we get this other formula on the left that addition must satisfy. And then you can play the same game with other properties like scalar multiplication. And then if you do this, you end up with a list of 7 axioms that your family must satisfy to be considered a divided power structure. One very simple example is that if you have a Q algebra R, then on any ideal of this Q algebra R, the only divided power structure is going to be the one given by the family x to the n over n factorial. There are also some other examples that are not the trivial one, but this example is going to be important later in the talk, which is why I'm mentioning it here. And we formalize this definition of divided power structure, and we also formalize a lot of the basic related theories. So we formalize the notion of divided power morphisms, subdivided power ideals. Also, we formalize some constructions like divided power structures on sums of ideals or on Gaussian rings. And all of this is summarized in a paper that we published in ITP 2025. But today I'm not going to focus on this basic part of the theory. I'm going to talk about how we construct something called the universal divided power algebra. So what this is if we have a ring R and an R model M, then there's a unique, there's a divided power algebra, gamma R M, gamma R plus M, gamma, together with an R linear map from the module M to this gamma R of M, that has the following universal property. So if we now have any other divided power algebra Sj delta, where S is an R algebra, and we also have a map from the module M to the ideal J, which is R linear, then there is a unique divided power morphism from this universal divided power algebra to the divided power algebra Sj delta, such that the obvious commutative diagram, such that the obvious diagram is commutative. And this triple is called the universal divided power algebra. Okay, so this was first defined by Roby in the 1960s, and he defined this as a ring using generators and relations. So the generators are going to be given by, we are going to write them as x to the n, where x is an element in M and n is a natural number. And then on these generators, we impose these three relations, or these three families of relations. And if we do that, we get the underlying ring of the universal divided power algebra. And if we look at the ideal generated by the generators of the form xn, where x is an element in M and n is at least 1, then we get the ideal corresponding to the universal divided power algebra. So this ring is easy to formalize as a ring. We just do this as by considering the multivariate polynomial ring, where the variables are indexed by pairs xn, where x is an element of M, n is a natural number. And then we just formalize this list of relations, and that gives us the ring that we want. Similarly, getting the ideal is easy. And it's also relatively easy to show that if we consider that the element xn has degree n, then these relations are homogeneous, and we get that gamma R of n is a graded algebra. Moreover, we can prove, and we have formalized that the 0th component or the 0 degree part is isomorphic to the ring R. The degree 1 part is isomorphic to the module M. And if we want to understand the R module structure of the n degree part, we can do this by studying something else called polynomial laws, and this will come back later in the talk. So the hard part of all of this is showing that there exists exactly one divided power structure, gamma, on this ideal, with a property that gamma n of x is equal to the generator xn for every x in the ideal and any n in the natural numbers. Now, showing the uniqueness of this divided power structure is easy, but showing that such a divided power structure exists is actually a hard theorem, and this was first proven by Robbie in 1965. I will not give all of the details of the construction today because this construction is very technical. It is very often treated as a black box in the literature. But I want to mention some places where this is used because this is a very important tool in modern arithmetic geometry. So this was used by Berthelot to develop the theory of crystalline cohomology. And this is also needed to define the Fontaine period ring decrease, which is being used in p-adic theory and also in some comparison theorem between different cohomology theories. So yeah, this is a very important object for arithmetic geometry, but also it's very often treated as a black box. So it was especially important to formalize this construction. And in fact, when we were formalizing it, we realized that there was a mistake in the construction of Robbie in the paper in 1965, which is the only full construction in the literature, although we will see that there are some other sketches that can be found. Okay. So I'll tell you a little bit more about the mistake that we found. So this is a paper that Robbie wrote in 1965. The error is in lemma 8 of this paper. And the proof of this lemma starts by saying that we know that there is an isomorphism of our algebras between this tensor product and this universal divided power algebra. But in fact, Robbie here is forgetting to tensor M with R inside this gamma. So that means that this is not really an isomorphism in general. So because of this, this breaks the proof of lemma 8, and this lemma is later used to conclude the existence of the divided power structure. So this proof breaks down. We cannot just copy the proof of Robbie's because it is not correct. However, we are able to repair this proof by essentially using the same main ideas that Robbie was trying to use in this paper. And we have formalized a complete proof. I will tell you a bit more about it. But I will also mention that Robbie later published a different construction of this divided power structure. And also there is another sketch by Berthelot and August in an appendix to their book on crystalline cohomology. But yeah, all of these proofs are different. So the proof that we ended up formalizing is in some ways similar to the proof or a sketch in Berthelot and August, but it's not exactly the same proof. There are some differences. And in fact, the proof that we ended up formalizing is a bit simpler than the one that they give. So I will very quickly give you an idea of the proof that we have formalized. And this is a very quick sketch. If you want to see all of the details, you can go to the link code or to this paper that I mentioned here. But the idea is we want to reduce to the case where M is a free C module or a free abelian group. So if M is a free C module with a basis which might be infinite, we are not assuming that this basis is finite, then the first thing that we have to do is we have to prove that this divided power algebra gamma set M is free with basis given by products of generators of this form, where Bi is an element of basis and Ni is the product of Ni is an element in into Bi or into J, I guess. So to prove that this is the basis, what we ended up doing is we identify gamma set of M with set subalgebra of the polynomial ring in the variables indexed by iota with coefficients in Q. And so this is the subalgebra, which has basis given by these products of elements of the form xi to the ni divided by ni factorial. Okay, so once we have the basis for the case where M is a free set module, we can then generalize to free R modules over any commutative ring R by applying some base change argument to get the basis for gamma R of M. And then in the general case, where we have a general R module M, in that case, we can deduce it from a quotient map from a free R module. So we use a presentation of the module M to relate this to get a quotient map from a free R module. We have to prove that the kernel of this quotient map is a subdivided power ideal. And if we do this, we prove a general theorem that in this case allows you to construct divided powers on the image. So that's how we get the divided power structure in the general case. And so this part of the story is summarized in a paper that we just presented at CPP last week. So this is formalizing polynomial laws in the universal divided power algebra. But in this paper, we were not telling the full story because at that point, we had formalized part of the constructions of divided powers. So we had reduced the case where M is a free R module, but we hadn't finished the proof in that case. So we hadn't constructed, we haven't provided a proof that the basis is what we say we are in this case. So we didn't have a complete construction. But last week, after CPP, I stayed for a few days with Antoine to work together on the rest of the proof. And we were actually able to finish everything yesterday. So since yesterday, we do have a free construction of the universal divided power algebra. So now that we have this, our next steps will be, well, first to clean up the proof, then construct some other universal construction, which is the divided power envelope. And then using the divided power envelope, we will be able to define the ring decrease. Okay. Now I will switch over to talking about polynomial laws for a little bit. So the idea here is if we have a map, say from R squared to the real numbers, which is determined by a polynomial. So there exists a polynomial into variables such that f of xy is just obtained by substituting the pair of elements xy into the variables. Then in this case, since the reals are an infinite set, we can prove that this polynomial is uniquely determined by the map f. And also we can use this polynomial to extend the map to other contexts. Right? So if instead of taking a pair of real numbers, we take a pair of complex numbers, then this will determine another complex number C. And then more generally, we could take a pair of elements in some R algebra and get an element in that R algebra. So the notion of polynomial laws is going to generalize this kind of map. So we generalize in two ways. So first, the real numbers are going to be replaced by any commutative ring. And then the vector spaces R squared and R are going to be replaced by arbitrary R modules M and N. And the definition that we can give in this case is that a polynomial law from the R module N to the R module N is consists of giving the datum for every commutative R algebra S of a map Fs from S tensor M to S tensor N, such that the obvious diagrams have to commute. So we have this compatibility condition for every pair of R algebras S and S prime related by isomorphism. Okay, so it's not very clear from this definition why we call this a polynomial law, but in fact, if you start with any finite family of elements in your module M, then there is a unique polynomial associated to this family that's going to determine the image of this map. So this is why we call it a polynomial law. And because of these connections with polynomials, we have notions of coefficients, of homogeneous polynomial laws, and also of differentials and partial derivatives of polynomials. Okay, so we formalize the definition in Lean as follows. So I'll first show you the code, and then I will discuss some ways in which the formal and the informal definitions are a bit different. So here we have R, M, and N. So R was the ring, and M and N were the R modules. And then for each R algebra S, we have a map from S tensor N to S tensor N. And then we have the functoriality condition that has to be true. Okay, so yeah, the first point where the informal and the formal definitions diverge a little is that in the informal definitions, we always take R to be a ring, but in the formalized definition, we allow R to be a commutative semi-ring. So maybe there is not a subtraction in R. And then similarly, we allow all of the R algebras S and S prime that appear in these two fields to be commutative semi-rings. Now, of course, this raises the question of if we start with a commutative ring R, is it true that the two definitions agree? And the answer is yes, because in this case, all commutative R algebras are going to be rings again. And we can put a commutative ring instance on any such S by using this commutative semi-ring to come ring construction. The only minor issue here is that if S is already a commutative semi-ring from the beginning, then the instance that we get this way is not definitionally equal to the original one. So in some proofs, we have to do a bit of work to check that these instances are actually the same. The next point where the definitions are a bit different is that in the formalized definition, we have to be careful with universes, which is something that is overlooked in Robbie's paper. What I mean by this is that in Robbie's definition, he's quantifying over all our algebras, but of course, this is going to lead to some kind of Russell's paradox if you are not careful, right? And in fact, if we go back to our definition here, we see that we have to put, if R is living in some universe level U, we have to also fix the same universe level for S and X prime appearing in these fields. But then later we can use some argument to actually generalize this to any R algebra living in some other universe V. The argument that we use is that any element in S tensor M is going to be given by a finite sum of elements of the form Sj tensor Mj. So that means that this is induced by some element in some smaller X prime tensor M, where S prime is some smaller algebra. So in the formalization, we take S prime to be the R polynomial ring in finitely many variables, which this is automatically recognized by Lean as living in the same universe level as the ring R. So this doesn't take a lot of Lean code. It takes about 200 lines in total, but yeah, this is something that was completely missing in the original paper. Something else that takes a lot more work in Lean than in the original paper is that Robbie in the paper makes many identification between objects that are isomorphic in, let's say, a canonical way. So this is just one example taken from the paper, but there are several instances where this happens. So in this example, R is again a commutative ring, S is an R algebra, and M is an R module. Then Robbie writes the following equality. So he writes M tensor, the polynomial ring in n variables over S, is the same as M tensor S tensor with the polynomial ring in n variables over R. Now, of course, Robbie knows that this is not really an equality. This is only an isomorphism. In fact, it's the composition of these two canonical isomorphisms. But he really does treat this as an equality. So sometimes he might start with an element on the left and then treat this as an element on the right-hand side without any further explanation. And of course, in Lean, we cannot do this. In Lean, we actually have to apply the isomorphisms if we want to be able to follow the same kind of arguments. And then last point that I want to make about implementation details is that, well, this is just copying the definition of polynomial law again. But in this definition, we were trying to get him to automate certain proofs for us. So we have this iscompat field here, which, remember, this is just the functoriality property that has to be true for pair of our algebras connected by a morphism. And we were hoping that if we try to use by ASOP here, this will take care of some of the easy cases. But what ended up happening is that this only worked in the trivial case. So this only worked for the constant polynomial laws. But even for the next easier case, which will be taking the polynomial law induced by a linear map, this was already not enough for Lin to get this. We actually had to provide the proof by hand. Okay, so I will conclude here. So I just want to summarize that we have formalized a construction of the universal divided power algebra. This is avoiding the error that appeared in Robbie's proof in 1965. And once we write this up, this is going to be the first complete and correct proof of this construction in the literature, because, as I said before, there are some other sketches, but none of them provide all of the details. Also, while working on this, we formalized the basic theory of polynomial laws. And one big takeaway that we have from this project is that we are going to need better ways to treat with these invisible mathematic issues if we want to make formalization of arithmetic geometry feasible. These are the main references that we follow. So we have 3 papers of Robbie and then also 2 books by Berthelot and August. And if you want to check more details, you can check our 2 papers, or you can also go to our repository and check if we have indeed sorry reconstruction of the universal divided power algebra. Yeah, that's everything. Thank you very much for listening.